At Mach 25, the kinetic energy of a reentry vehicle converts into thermal energy, generating heat fluxes exceeding 10 megawatts per square meter. This extreme environment necessitates thermal protection systems that do not merely insulate, but actively manage energy dissipation. Ablative shields are the primary solution, functioning by sacrificial mass loss. As the outer layer heats, it undergoes pyrolysis, sublimation, and melting. This process is endothermic, absorbing massive amounts of energy, while the resulting gas layer, or Char layer, acts as a boundary layer coolant. The material selection is critical, balancing low density for reduced mass fraction against high heat of ablation. The defense industry relies heavily on proprietary carbon-phenolic composites and specialized materials like PICA, or phenolic impregnated carbon ablator, originally developed for NASA but now essential for maneuvering reentry vehicles where precise shape retention is less critical than total thermal load management. Carbon-phenolic materials dominate the ablative market due to their high carbon yield upon pyrolysis. When heated, the phenolic resin decomposes, releasing gases like hydrogen and methane, which push the boundary layer away from the surface. The remaining carbon structure forms a robust, porous Char layer. This Char layer is crucial. It insulates the underlying structure and provides mechanical stability against high shear forces encountered during atmospheric deceleration. Manufacturing these shields involves complex processes, typically filament winding or molding, followed by high-pressure curing cycles lasting weeks. The uniformity of the material density and the precise control over the fiber orientation directly impact the shield's performance and reliability. Defense contractors must maintain strict quality control, as even minor voids or inconsistencies can lead to catastrophic localized failure, known as spallation, compromising the warhead or payload integrity. The supply chain for ablative materials is highly specialized and tightly controlled, often involving only a handful of qualified suppliers globally due to stringent defense specifications. Key precursors, such as high-purity phenolic resins and specific carbon fibers, face long lead times, sometimes exceeding 18 months. This scarcity drives up unit costs, making the thermal protection system a significant fraction of the total reentry vehicle manufacturing expense. Procurement contracts often mandate dual sourcing or require contractors to invest in maintaining domestic production capabilities to ensure strategic resilience. Furthermore, the intellectual property surrounding the precise formulation and manufacturing techniques of advanced ablators is heavily protected under International Traffic in Arms Regulations, or ITAR, restricting export and collaboration, thereby limiting market competition and maintaining high barriers to entry for new defense players. Plasma blackout is an unavoidable consequence of high-speed atmospheric reentry. The intense shock wave ahead of the vehicle compresses and heats the air to temperatures exceeding 10,000 Kelvin, causing the gas molecules to ionize into a dense plasma sheath composed of free electrons and positive ions. This plasma layer acts as a Faraday cage, effectively blocking radio frequency signals used for telemetry, guidance updates, and tracking. The critical factor determining signal blockage is the plasma frequency, which is directly proportional to the square root of the electron number density. If the plasma frequency exceeds the frequency of the communication signal, the signal is reflected or absorbed. This blackout period typically lasts between 30 seconds and 3 minutes, depending on the vehicle's trajectory and velocity profile, creating a critical vulnerability window for defense systems.
Defense contractors employ several sophisticated techniques to mitigate or shorten the plasma blackout period. One approach involves injecting electronegative gases, such as sulfur hexafluoride, into the plasma layer. These gases capture free electrons, reducing the overall electron density and lowering the plasma frequency, thereby allowing higher frequency signals to penetrate. Another advanced, though complex solution involves using magnetohydrodynamics. Powerful onboard magnets generate a localized magnetic field that alters the electron mobility within the plasma sheath, creating a window through which radio waves can pass. Furthermore, shifting telemetry to extremely high-frequency bands, specifically the Ka band or higher, helps bypass the plasma frequency threshold, although this requires more powerful transmitters and highly directional antennas on the ground and the vehicle. Traditional intercontinental ballistic missile reentry vehicles follow predictable high-angle trajectories, resulting in a short, intense thermal pulse. Hypersonic Glide Vehicles, or HGVs, however, operate at lower altitudes and maintain high speeds for extended periods, leading to a prolonged, lower-intensity thermal soak. This difference fundamentally changes the engineering requirements for the thermal protection system. HGVs require materials with superior long-duration oxidation resistance and creep strength, often favoring ultra-high-temperature ceramics, or UHTCs, over traditional ablators for leading edges. The shift toward HGVs is driving significant defense investment into new material science research and specialized manufacturing facilities capable of handling these complex ceramic matrix composites, creating a new high-margin market segment focused on sustained thermal management rather than single-use ablation. Validating thermal protection systems require specialized, extremely expensive ground testing infrastructure. Arc jet facilities are essential, simulating the high enthalpy and shear stress of reentry by passing high-power electric arcs through gas streams. These facilities, such as the NASA Ames Arc Jet Complex, are critical bottlenecks in the defense development cycle. Access time is costly, often exceeding tens of thousands of dollars per hour, and is highly competitive among prime contractors. While computational fluid dynamic simulations are used extensively for initial design, they cannot fully replicate the complex thermochemical reactions and material recession rates observed in real-world plasma environments. Therefore, physical testing remains a mandatory requirement for flight qualification, driving a niche but high-value market for specialized testing services and instrumentation capable of measuring surface recession in real time. The technology governing ablative shields and plasma mitigation is classified as Missile Technology Control Regime, or MTCR, Category 1, placing it under the strictest export controls, primarily the United States ITAR. Any transfer of technical data, manufacturing know-how, or even verbal discussions with foreign nationals requires explicit government authorization. This regulatory environment significantly increases compliance costs for defense contractors, necessitating dedicated legal and security departments. The risk of unauthorized technology transfer is extremely high, leading to severe civil and criminal penalties, including multi-million-dollar fines and loss of export privileges. Consequently, companies operating in this sector must implement robust internal controls, limiting collaboration even with allied nations unless specific technology transfer agreements are in place, thereby segmenting the global defense market. Future investment in reentry technology focuses on moving beyond passive ablation toward reusable or actively cooled systems. Ultra-high-temperature ceramics, particularly hafnium and zirconium diborides, offer superior resistance to oxidation and thermal shock at temperatures up to 3,000 degrees Celsius, making them ideal for reusable spaceplanes and advanced hypersonic vehicles. Furthermore, research into active cooling systems, where cryogenic fluid circulates beneath the surface to absorb heat, promises near-zero material loss, although the complexity and weight penalty remain significant engineering hurdles. The current geopolitical landscape ensures sustained, high-level defense spending on these technologies, particularly in strategic missile modernization programs. This guarantees a stable, long-term revenue stream for the few prime contractors and specialized material science firms dominating this critical sector.